but we are looking forward to your presentation. Thank you very much.
Thank you. So I'm not sure exactly what you see on the screen, so maybe you can help me as I, does that go into presenter view or the full screen?
Now it is the presenter view, what we are seeing.
Okay, so maybe.
Now it is the full screen.
This is good? Okay.
Mm-hmm.
Thank you. Thank you, Gonzalo. And I'm very sorry about the time confusion. I don't know exactly what happened, but I'm sure it's my fault. So I appreciate that Victor was able to swap with me last minute. Again, apologies to the organizers and everyone in the audience. But yeah, so thank you. Thank you very much for the invitation. I'm really happy to be talking to everyone today. So this was the original title of my talk, Rheology of Cement Paste with Nanoparticles. And I am still planning to talk about rheology of cement paste. But I noticed the topic of the seminar, which is cement-based materials and sustainable construction. So if everyone doesn't mind, I wanted to update this to microparticles, and microparticles derived from CO2 mineralization. So we recently, we're wrapping up a study right now on this topic. So this was a 3-year study, and we really have a lot of interesting results. And I'm going to present a subset of that, really focusing on the rheological aspect. So I think this audience probably knows what concrete is, but this is just a slide that I made recently that I'm very proud of. So I just wanted to share it. This is just an excuse. But you know, concrete is volumetrically mostly aggregate. But we know that cement is the key ingredient, which combined with water undergoes a chemical reaction, and that really forms a binder that binds all the materials together to create this composite material. And we introduced air for durability purposes, but there's also entrapped air during the mixing process. But by combining all of these ingredients under ambient conditions, we know that we can develop or produce this incredible structural material. And we all know that concrete hardens through a series of reactions. And so as a result of that, it undergoes various phase changes, really incredible, becoming or starting as a fluid, flowable material. So it really moves during construction, but then a few hours, days, and weeks later, it turns into this rock hard material. And this is because of these series of chemical reactions, right? And so I think a number of us who are speaking today, and maybe some of you in the audience, you know, concrete is typically thought of while it's in the hardened state, which is of course important, but the fresh state, even though relatively it's a short period of time, is really important because it will determine the eventual performance of the structure in place, but it also will govern how efficiently, how well construction goes. So it really has a significant impact on constructability. And that's really changed the way we build today. So there's been a lot of innovations in material science, in cement-based materials, and that really has a direct impact on construction. And so we've been interested sort of in high performance for a very long time, you know, so for a while it's really been focused on stronger and stronger concrete, which is important, and we've made significant progress there. But now we face different challenges, right? And I think we are all aware of this, but just in case, you know, cement production emits significant CO2. And one of the reasons for this, or the key reason for this, is because we use a carbon-containing raw material. So limestone is one of the key feedstocks materials for Portland cement production. And so we calcine calcium carbonate, right? To obtain calcium oxide, which is the calcium that we want for Portland cement or clinker. And just through the chemistry, there's direct emission of CO2. And of course, the calcination is done because we burn the material, right? And so we burn this massive cement kiln to temperatures of 1450 degrees Celsius. And so, of course, there's thermal emissions associated with this, where we utilize fossil fuels. So combining the direct and indirect emissions, there's about 0.7 tons of CO2 per ton of cement. And so when you compare it to other building materials, that's not that high, right? Compared to steel, it's not that high. But when you combine it with just the massive amount of cement and concrete we produce, that's how it all adds up. Where concrete is the largest by mass commodity market. We produce over 30 gigatons of concrete per year, and that results in more than 4 gigatons of CO2 per year, where most of that is tied to the cement production. So it's considering all of that, where it results in 6 to 8% of global anthropogenic CO2 emissions being attributed to cement production. And that's not going to go away, right? Concrete is here to stay. The demand isn't going to go down. It's only going to go up due to continued urbanization, the need to repair and build new infrastructure. And so that's why there's just so much emphasis on how can we decarbonize the sector? How can we adapt more sustainable practices? So there's multiple pathways to do this. And the most immediate is likely clinker substitution. So we already use SCMs, fillers in the industry and practice, and we can kind of keep pushing that limit and maximize the substitution of carbon intensive cement with clinker. But there are other technology pathways that are out there. And if we're really serious about decarbonization, then we have to do more than replace clinker. We have to embrace entirely new technologies. And one of them that we've become interested in recent years is carbon capture, utilization, storage, with a focus on utilization and storage. So this is a visual that depicts the potential of CCUS in various industries. And you see circled in blue, we have construction. And so this can be done through CO2 mineralization to produce construction materials. So through CO2 mineralization, gaseous CO2, so emissions-based CO2 can be converted to solid carbonates. And those solid carbonates, for example, calcium carbonate, can be used as either a cement replacement, right? We already use that today as limestone filler, or aggregate replacement. We already use limestone as aggregate. And so, and just a last point, and the reason, again, that there's so much potential here is that, remember from the last slide, we produce such a massive amount of concrete, right? So that's a significant storage potential, volumetrically, mostly in the aggregate, but then there's also the opportunity to replace that carbon intensive cement with these synthetic fillers and SCMs. So for CO2 mineralization, you need some sort of alkaline feedstock. You need something to employ the mineralization on. So if you look at potential feedstocks, there's calcium or magnesium bearing silicate rocks. So whatever, we just want to stop using limestone or minimize the use of limestone, because if we start off with a carbon containing raw material, it's very difficult to reduce emissions. So folks are looking at other sorts of geological materials, including these calcium silicates or magnesium silicates. They're available in vast amounts, regionally pretty widely available. But there's parasitic energy consumption because these materials, as geological formations, they do require mining. And also they have a relatively low reactivity. And so they would need some kind of mechanical or chemical activation. On the other hand, alkaline solid wastes are highly reactive. So those are your fly ashes, red mud, construction demolition waste, slags. Those are all industrial wastes, and they, thermodynamically, it's favorable for them to carbonate. So they're kind of this ideal feedstock from a chemical point of view, but also from a practical standpoint, industry waste often coexists with industrial CO2 point sources. So the potential to minimize or eliminate transportation. And so people are considering this, and a lot of work has been done relatively on fly ash and slag, but less on waste concrete, specifically the paste phase, and that's what we are working on in our team. And so the advantages of this, of upcycling demolished concrete and employing it into a CO2 mineralization scheme, is that there's emissions reduction, right? There's waste management, and reduced mining. You don't need to mine for this feedstock material. And importantly, just on the right as a note, this is just kind of showing all the different feedstocks, because when you're coming up with some kind of alternative solution, you have to make sure that there's abundant availability, because again, our consumption of cement and concrete is so significant. So there's industrial waste and CO2 mineralization. So you can kind of combine these two concepts. So you can upcycle industrial waste via CO2 mineralization. So this is kind of like a high level framework, or the framework at a high level. So you start with industrial waste, and they're rich in calcium, silica, aluminates, so all the things that we like to see in cementitious materials, right? And then we can employ CO2 mineralization. So this can take on various forms, single versus multi-step. I'm going to show our example, which is multi-step. Basically, this is where, importantly, CO2 is an input, and you employ carbonation. And as a result of this process, this chemical process, then you can produce the synthetic SCMs and or fillers. And because of the chemical process, by tuning the parameters, there's this potential, this opportunity to tailor the properties of these SCMs and fillers. So this can be quite engineered. And then those SCMs and fillers can then be incorporated into concrete production. Yeah, and so another note, so I emphasize that clinker substitution, that's the direction that we have to go in. And that's kind of the more immediate solutions that we can implement right now. We already do it, we can maximize, but some of the SCMs that we utilize today, like coal fly ash, those are just going down in supply because we're reducing our reliance on coal as an energy source, which is good, but it's taking away a material that we like and that we're comfortable with. But because of the decrease in the supply, that's why there is a need to sort of start to explore other emerging and novel SCMs and fillers. And so I think this would fall into that category. So in our work, we looked specifically at construction and demolition waste, specifically the paste phase. And basically, we employed extraction and mineralization schemes. In a later slide, this will be shown more in a little bit more detail. But we basically extract the calcium, right, because that's going to be in the recycled cement paste, and employ CO2 mineralization to produce calcium carbonate. So basically a limestone filler, and then that can be used for concrete production, incorporated into built environment. And so, this sort of framework allows for essentially permanent CO2 storage, reduction in cement use because we're replacing OPC with this limestone filler, and a circular economy. So in our work, we employed a two-step CO2 mineralization scheme. And so what does this mean? So you start off with your feedstock, which in our case is C&D concrete waste. And then we employ this two-step extraction and carbonation process. So basically what this means is we employ a pH swing. So first we introduce an acidic source, and that lowers the pH, and that allows us to extract calcium. And then what you have is this leftover silica-rich residue. So you should be thinking, okay, that is a source of an SCM. And then you employ this pH swing. And so you introduce a base, and then that increases your pH. And then from there, you can start to remove additional impurities. So remaining silica, remaining iron, alumina, and that creates the secondary residue, what we call the precipitate. Volumetrically, it's much less than the residue, but that also has some silica, so a potential candidate as an SCM. And then finally, from this two-step process or the pH swing, then you've sort of removed most of the impurities, and then you're left with calcium. And then you apply the carbonation, and you can produce high purity carbonates. So in this two-step extraction and carbonation process, you end up with two products. One is a silica-rich material, and that can serve as an SCM. And then the other is a high purity carbonate, which can serve as a filler. And importantly, by tailoring the parameters of the process, you can produce different polymorphs with very distinct morphologies, and that can lead to different functionalities when you introduce it into cement. So the SCM, the silica-rich residue, we tested it. We tested the precipitate and the residue, and we see it doesn't outperform silica fume because silica fume is just such a pure form of silica. But we do see that there is this pozzolanic reaction where there is increase in the long-term strength gain. And with the high purity carbonates, there's three polymorphs. So we'll talk about this in detail. This is just giving you a glimpse. But because of the distinct morphologies, even though they're all calcium carbonate, they affect cement hydration kinetics differently. So there is going to be an impact on the cement base system. And just as a note, we focus on the two-step extraction and carbonation process, but there's also direct processes as well, where you just kind of bubble CO2 directly, or like the dry method would be subjecting your powder to an accelerated CO2 condition and controlling the relative humidity, relatively high humidity. And in that case, you get a single product where the carbonates and the silicate co-produce. So you get this one product, but you still get the carbonate, and then you're still left with this pretty reactive pozzolanic material. So one step, you get one product. Two step, you get two separate products. It really depends. I mean, there's pros and cons in both. Obviously, the direct process is much more straightforward. It's one step. But in the two step, you get these two materials with higher purity. Okay, so this is actually looking at what the process looks like. So you start off with this recycled cement paste powder, and then you drive down the pH, and then you extract out your calcium, and then you have this silica-rich residue left over. So that is our candidate SCM. And then you employ this pH swing where you drive the pH back up, and then that's where you extract out your precipitate. And so that's where, again, the remaining impurities are. So silica, alumina, iron, a little calcium gets in there. But then you have a pretty pure calcium system. You apply CO2 bubbling, and you get your calcium carbonate. So chemistry is pretty amazing, where you start off with this cement paste, this recycled hydrated cement paste, and then you can separate the silica and then obtain this very pure form of calcium carbonate. So I mentioned that by kind of adjusting the parameters of this process, you can form different polymorphs. So these are all calcium carbonate. And in nature, calcite is what we typically see. So the limestone filler that we use in construction, that's all calcite. And the reason is because that's the most stable form. That's the stable form of calcium carbonate. But then there's also other forms, metastable forms, vaterite and aragonite, which rarely are seen in nature. I think aragonite is seen very limitedly in nature. Vaterite pretty much not at all, as far as I understand. Sorry, I keep. But what's cool for us is that, okay, through this process that we have the opportunity to form these different polymorphs, and they look very different, right? So calcite is cubic, vaterite is spherical and porous, actually, and then aragonite is needle-like. And, given the different morphologies, as expected, you see these very different values in terms of the VT surface area, where aragonite has the highest, vaterite the second highest, because vaterite is porous, aragonite is needle-like, so high specific surface area and high aspect ratio. And then with the particle size distribution as well, in particular, the aragonite has a finer PSD. And so some literature has already started to explore this, where aragonite has been found because of its needle-like shape. It can have reinforcing effects, and vaterite, because they're porous. The previous speaker mentioned internal curing. They may have the potential to absorb water and have internal curing capabilities. So what's exciting is that, again, these materials can start to add functionality. And our work has shown that these polymorphs, these metastable polymorphs, are actually stable in cement-based systems. So if we want to use vaterite as these porous spheres, they'll remain as porous spheres in the cement-based system. Aragonite will remain as needle-like materials. So this isn't the main focus of the talk, but just wanted to give you an idea of how these impact very basic properties. So we like to study hydration kinetics. And so these are all cement paste with 20% replacement of calcite, aragonite, and vaterite. So those three different polymorphs. And we see that they all impact cement hydration kinetics differently, right? And so note that this is all normalized with respect to massive cement. So we're really focusing on the impact of these materials on cement hydration. And as expected, they all have a filler effect, right? So they all promote nucleation and growth. And so you see the shift and this increase in the peak of these hydration curves. And aragonite has the highest peak. And we can likely just attribute that to the increase in specific surface area, where they have more surface area for CSH nucleation to occur. We also looked at cumulative heat release. And so on the left, it's again normalized with respect to cement. And here it's interesting because over time, initially the aragonite has the highest cumulative heat release, but then it starts to crosses over around 24 hours, where calcite then exhibits the highest cumulative heat release. And I don't include the results here, but we found that calcite actually has the most reactive surface. And so although aragonite has higher surface area, calcite has the most reactive surface. And so that may be coming into play at longer time periods. But ultimately, we're interested in what is the impact on mechanical properties, specifically compressive strength. And so if we want to start getting an indication of that, we normalize with respect to total solids. Right. So up until now, I've been reporting the results for hydration kinetics and cumulative heat release with respect to massive cement. But now we're going to do massive solids. And the cumulative heat release there will be an indication of mechanical strength. And so once we do that, then we see that ultimately OPC does exhibit the highest cumulative heat release. And that is because, calcium carbonate is going to be a less reactive material, right, compared to OPC. So there's going to be that dilution effect. And we see similar trends in compressive strength gain. So these are the compressive strengths of pretty much the same material systems that I've shown thus far. So OPC compared to calcite, aragonite, and vaterite at 10 and 20%. And basically what we see is that OPC is the highest by 28 days, and the others are comparable. There's no real measurable effect, at least by the method that we use, which was 1-inch cylinders due to limitations in the material that can be produced. But, as a limestone filler, this is an expected trend, so it's not behaving any differently from what we use today. And with PLCs, with Portland limestone cements, we know that to achieve the comparable strength gain or the target strength, we can apply grinding, right? So PLCs are typically finer than OPCs because the finer the limestone is, the more reactive it can be, where it can contribute to a filler effect. So if needed, we can also apply those sorts of principles here as well. But as is, no improvement in the compressive strength. They all perform comparably. But I mentioned that, vaterite might be an internal curing agent. Aragonite might have reinforcing effects. We haven't explored that. We'd be curious to do so if anyone else wanted to. But of course, as in our group, we're just interested in flow behavior. So we wanted to look at, well, these all look very different and there must be an impact on rheology. And so that's what we focused on. So this is our rheological protocol. So we did focus on the cement paste phase. So we can use a stress controlled rotational rheometer, fix the water solid ratio, use a vane geometry. And so this is our protocol here. We apply a pre-shear, and that is so that we get to some reference state across all samples, across all tests. And we were interested in the evolution of various properties, including the static yield stress and the dynamic yield stress. So we imposed different rest periods from 0.5 minutes to 30 minutes. And then we applied an intermediate shear rate, so relatively slow shear rate over 600 seconds. So when we apply the pre-shear, we looked at the viscosity decay. When we impose the intermediate shear rate, we got this stress evolution, right? So this is kind of a typical depiction of the flow response. So you have this initial sort of elastic component, and then there's this peak, and that indicates flow onset. So there's visible deformation of the material, and that indicates your static yield stress. And then if you continue to shear your material, then it eventually reaches a steady state, and that can be considered as your dynamic yield stress. So that's the minimum stress that's needed to keep your material in motion. We're interested in both of these values. So static yield stress is the stress needed to initiate flow. Dynamic yield stress is the stress needed to terminate flow. So these are the results. So impact on viscosity and static yield stress evolution. So this is what we obtained during the pre-shear. And so compared to OPC, there's some increase with the vaterite and calcite, but then there's this pronounced increase in the dynamic viscosity when you introduce the aragonite. And to mention, all these materials have the same specific gravity, so we can assume that they had the same solid volume fraction. So there's this jump in viscosity. And then we impose the intermediate strain rate at various rest periods, and these are typical responses. So again, the calcite and vaterite seem to have minimal effect on rheology, but then with the aragonite, there is this significant increase in this peak, which can be taken as a static yield stress. And so we took that peak and then measured it over time. And these are including error bars. So there's this dramatic difference, right, in the flow response of paste with aragonite addition compared to calcite and vaterite. And we're going to talk about why that is. But just to talk about what the actual impact is on rheology, it increases viscosity, but it really increases static yield stress and also the rate of increase of static yield stress over time. And it seems like Professor Roussel already talked about the thixotropy index, and so did Victor. He referenced it. We also measured that, and it was, an order of magnitude higher. So there's something where the aragonite is impacting the rheology very differently. And this is just to focus in on the calcite and vaterite because it gets a little squashed. But really no really significant change on static yield stress evolution compared to OPC with no calcium carbonate replacement. We also looked at what is called what some have called the thixotropy index. So just kind of an idea of what is the relative degree of structural buildup versus structural breakdown, right? And so we have static yield stress evolution up here. So this is the same result as the previous slide. And then dynamic yield stress evolution at the bottom. So remember, that's your steady state in your flow curve. And the ratio between this can be taken to be a thixotropy index, because the static yield stress gives you a measure of like the structural buildup, and then the dynamic yield stress gives you a measure of the structural breakdown. And again, we're seeing the same trend, right? So it does increase dynamic yield stress, but relatively the increase in static yield stress is very, very significant. So aragonite is introducing this very interesting behavior, and we wanted to understand why. So what I'm going to present is we looked at the effect of geometry, and then we also looked at the effect of hydration. So what do we mean by geometry? So here we're focusing on the effect of geometry. And by geometry, I mean the particle shape and the particle size distribution. And so just remember those SEM images of all the different polymorphs. They're very different, right? In particular, the aragonite is very different. They're needle-like. And so to really isolate this effect and remove the effect of hydration, because I'm so sad to have missed Nicholas' talk, but I'm sure Professor Roussel emphasized that, the progression of hydration, even though we are in the dormant period or the induction period, it will have an impact on your fresh state properties, on rheology. So we want to eliminate that, and we did that by replacing water, which is critical for the hydration reaction, with a nonpolar organic solvent, kerosene. And so by replacing water with kerosene, we eliminate cement hydration. And also there's no dissociation or dissolution of the cement phases. So that means there's no charging effects either. Okay, so we eliminate the effects of hydration, and then we measured static yield stress. So here we're reporting the same measurements from before. So the light gray is the cement water systems, the paste. And then the dark gray, those are the cement kerosene systems. And so what we're seeing is, okay, even without the effect of hydration, aragonite is leading to an increase in static yield stress compared to the other polymorphs, calcite and baterite. So there's definitely a shape effect, size effect. And so, the way we sort of visualize this is aragonite, they're needle-like. And because of the increase in specific surface area, they're able to aggregate together. And so through that aggregation, on the onset of flow, they can impose this resistance to stress. And so that's why it's driving up that static yield stress so much. There's also the impact of higher water demand due to the higher specific surface area. So all tied to shape, right? And because of these shapes, it also interrupts the flow line as well. So that's the reason why static yield stress is higher for aragonite. But then we also measured that the thixotropy index is very high, right? So relative to static yield stress, the dynamic yield stress is pretty low. And that is because, and this is found in all sorts of suspensions with needle-like materials. Under flow, these fiber-like or needle-like materials can align in the direction of flow. And we suspect that the same thing is happening with the aragonite. With increasing shear duration, more and more of it can break down and align in the direction of flow, which is why we can achieve pretty relatively low viscosity and dynamic yield stress while balancing high static yield stress. So that explains a little bit, but if you look at the values in the cement kerosene system, the static yield stress compared to, let's say, calcite, aragonite was 2 times higher, okay? But if you look at the cement water systems, it was 6 times higher. So this pointed to us that geometry isn't the only factor at play. So there's more happening. And of course, we looked into the impact of hydration. So now shifting from geometry to focusing on the role of hydration, we re-examine the isothermal calorimetry results. And we really focus in on the time window that matches up with our rheological tests. right? So before we looked at like full curves up to like 5 days, 7 days. But now I'm showing the full curve, but I'm highlighting the area that we focused in on, which is the time window for the rheological tests. And then that is what is blown up here. And so if you look at that, so this is the hydration kinetics, so rate of heat flow. Aragonite has the highest heat flow. And so again, that just indicates that aragonite, likely due to the increased surface area, it is having more of a filler effect. Okay, so we kind of already looked at that, but we're just now focusing in on the relevant time window. Okay, seeing the same thing. Now let's look at the cumulative heat release. So again, these are similar results from before, but now let's really focus in on the time window for the rheological tests. So remember that when we looked at it before, calcite actually, and this is by weight of solid, okay? So that's important. We're looking at the entire solid system. We're not just normalizing it with respect to cement. So this will give us an indication of basically the formation of early hydrates, right? And that's why this is also taken to be an indication of mechanical properties. So remember before we were kind of just focusing in on this area, or that's where I was pointing your eyes. But calcite has the highest cumulative heat release of all the systems with the calcium carbonate, right? But then remember there was a crossover point. So if we zoom in to the cumulative heat release and the time window for the rheological tests, then aragonite has the highest heat release. And so that points to us that, yes, this is a very early window. And I think there's maybe some discussion on how representative is this data. But for us, for comparative purposes, and we found this consistently in our results, it does indicate that it does have higher cumulative heat release than aragonite. And that translates to increased formation of early hydrates. And what that means is there's an increase in the solid volume fraction of our suspension, and that would then lead to an increase in static yield stress and other rheological properties as well. All right. I forgot what time I started, but since we're running, this may have been short, but I think maybe that's okay in terms of getting back on schedule. So this is my last slide. So some key takeaways. So calcium carbonate polymorphs exhibit different levels of reactivities, or they can. And supporting results indicate that it's both due to available surface area, but also surface properties. All the derived calcium carbonate particles or polymorphs had a similar effect on compressive strength gain. So we didn't really capture any differences there, but it would be really interesting to look at other properties and also scaled up because the scaling matters. So interested in tensile strength, durability, shrinkage due to other potential functionality. So again, all these polymorphs look very different and they may introduce beneficial properties outside of compressive strength. Focusing on rheology, aragonite exhibited the higher static yield stress, rate of increase, and thixotropy index compared to calcite and baterite. And we looked at the potential factors, and our results point to it's due to the geometric effect, the needle-like shape, and similar effects have been captured with nanoclays, which I've been working on for a long time, and hydration effects. So the filler effect, the enhanced filler effect, which results in early hydrate formation. So this is more of like a comment and to maybe inspire some of you. And emerging chemical schemes like the one I pointed to today, so CO2 mineralization. And importantly, I don't know if I mentioned this, but that is in partnership with a faculty member in chemical engineering who's an expert, or earth and environmental engineering, who's an expert in these CCUS technologies. So we team up with experts in chemistry because we're okay at cement chemistry, but not chemistry. But emerging chemical schemes from other disciplines open up the possibility of tailoring morphologies of synthetic fillers and SCMs, and those can be leveraged to control fresh state properties as well as hardening and hardened properties. So let's not forget the fresh state properties, because again, that is important for constructability. Okay, and so the ones who really do all the work, Jonah Williams, he does all like the mineralization, extraction work. He's in the Earth and Environmental Engineering department. And Dian Zhao, he's my PhD student in our civil engineering department, and he did all the cement characterization